Yeah, hi everyone, Mr. Markwick here. Today's video I'm going to show or go through a bit of an overview of the parabolas topic. Up here you can see I've obviously got quadratic equations and parabolas, so it's important to have an understanding of quadratic equations before trying to work through the parabolas section in your textbook or having a go at parabolas in general. Let's start with the basics. So we have started by looking at some key features of parabolas. So in terms of the x-intercepts, where that parabola crosses the x-axis. Right, now we know that parabolas can cross the x-axis at 2 points, at 1 point, or they might not cross at all. And we'll look later in this video, in fact, at what the equation is that determines how many times a certain equation may cross the x-axis, or how many intercepts an equation may have. The y-intercept, so the point where the parabola crosses the y-axis, every parabola will cross the y-axis at some point. Whether it's at 0, 0, or at another point, it will cross at 1 point. To determine the y-intercept, substitute into the equation x equals 0, no matter what form the equation's in, x equals 0, and that will determine the value of the y-intercept or the y value in the y-intercept. The turning point, so where that parabola begins to, turn around, its vertex we also use as a terminology. Okay, this is a minimum turning point or a minimum vertex. Parabola's opening upwards. And one thing that's not shown here is the axis of symmetry. So that imaginary line that splits that parabola in half. We know parabolas are symmetrical. So in this case, if one of those squares was equal to 1 unit, the axis of symmetry would be x equals 1 over 2, or 1/2, or 0.5, because that x value would be 0.5. Okay, so they're the 4 key features we're working with when we're talking about parabolas: the x-intercepts, y-intercepts, turning point, and axis of symmetry. I'm just going to put this as shorthand, axis of symmetry is that 4th key feature. Now, standard form of a quadratic equation. When we look at an equation, it may be in standard form. So, for example, y equals ax squared plus bx plus c. This is a quadratic equation, and we know that quadratic equations represent parabolas. Now, the example I've got there on the left-hand side, there's only one term, y equals x squared. Now, the value of a in that equation is actually positive 1. Remember, there's nothing there. We assume it's a positive 1. B is equal to 0, and c is equal to 0. All right, and that's okay. As long as a is not equal to 0, we can have a parabola. All right, so that's the most basic form of the parabola, of a parabola, most basic form of the quadratic equation, or of a quadratic equation, I should say. Now, this value of a can determine a few things. So let's just go through some examples. I reckon that's probably the easiest way to do it. So let's say if a is, in fact, that one I've got there is y equals x squared. A is equal to 1. If I change that value of a to, let's say, 2 x squared, what actually happens to that parabola is that it becomes narrower. Okay? If I decrease that value, so let's say y equals 1 over 2 x squared, the parabola actually becomes wider, or it dilates. All right? Now I'm just sort of roughly showing you, these aren't drawn accurately. I haven't plotted any points or anything like that. I'm just showing you how changing the value of a affects the shape of our parabola. Now, parabolas can also open downwards if a is less than 0. For example, if a is, let's say, minus 1, minus x squared, that one will be opening downwards. Okay, it'd be the same thickness as that first parabola that was drawn, y equals x squared. They're the same. In terms of the dilation, they're the same. One's opening upwards and one's opening downwards. All right. so that's pretty much what A does. It flips it, and it's responsible for dilation. Now, one thing we also spoke about, certainly in my classes, was how C affects the position of the parabola. C is responsible for vertical translation. And in the standard form, the value of C is, when you see a parabola that's in standard form, the value of C will determine where it crosses the y-axis. Okay, but that's only when it's in standard form, like this. So this is another example of standard form. So if I had y equals, let's just say x squared plus 3, here in this equation, A is equal to 1, B is equal to 0, but C is equal to 3. So I've only got two terms. I don't have that middle term as such, which is fine. My parabola is actually translated 3 units up, or the vertex is translated 3 units up. So it's actually the vertex will be at this point here, okay? And again, because A is positive 1, it'll be opening upwards. If I had, for example, let's do it in black here, y equals minus x squared plus 1. We know it's going to be opening downwards, but the vertex is translated 1 unit up to positive 1. Okay, so A will be responsible for, I guess, making it narrower or wider, the parabola that is, or if it's negative, opening downwards. If it's positive, opening upwards. The value of C affects that vertical translation of the parabola. And if that was, so for example, minus 1, then we'd actually be opening downwards from minus 1. Alright? Just to show that there. Now, that's standard form. Standard form is really good because that value of C, if there's a constant term, it tells you what the y-intercept is. Okay? If there's no value of C like this one, then the y-intercept's just 0. Okay? If there's no constant term, there's no value of C, y is equal to 0. Well, the y-intercept is 0, 0, I should say. Now, moving on to turning point form, which we've also looked at, which is y equals ax take h all squared plus k. Now, the turning point is good because it basically tells you where the vertex is just from looking at the equation. So the vertex is at the opposite value of h. So if it's minus h, it becomes positive h, and whatever the value of k is. So k stays the same, h, we flip it around. So if that was, for example, plus h, that would be minus h. Let's just keep it at that for now. Let's do two examples. I'm going to show you turning point form and how to, I guess, start by plotting the vertex or the turning point just from looking at the equation. So here's an equation, y equals, let's keep it simple. Let's keep a as positive 1 in both of these examples. X take 2 all squared plus 3. My vertex is at positive 2. See how that was negative 2, now it's become positive 2, and 3. Okay, so that's where the two values have come from. Positive 3. Alright, so if I was to plot that here, that turning point or that vertex, it would be at positive 2, positive 3, which is right there. Once you can work out your y-intercept, you could then, I guess, plot that. So for me, I'm not going to worry about substituting in x equals 0 if I wanted to work out my y-intercept. I'm just going to show you, I guess, it's going to open up like that. There wouldn't actually be an x-intercept for this one at all. That's a bit of a clue there, the plus 3. Anyway, let's look at another example. Y equals, so here we go, y equals, in turning point form again, let's just do x plus 4 all squared take, let's just do, I was going to do 3 again, let's just do take 2. So here we go, the vertex is at minus 4 this time, minus 2. So it's that sign, there's that sign that becomes the opposite of what it is. And this one remains the same. So -2 remains -2. Alright, so the vertex there would actually be at -4, -2. So -1, 2, 3, 4, -2 here. Alright, and this one would actually have two x-intercepts. Again, to determine what the x-intercept is, there's a bit of a clue there, the -2. To determine what the x-intercepts are, you'd have to factorize this by using difference of perfect squares. But I'm not going to do that in this video because I'm just going through an overview. Check out one of my other videos if you want to know how to determine the x-intercepts for that one there. All right, but again, that's the turning point. It would be opening upwards. It would cross the x-axis at 2 points. All right, guys. So that's what's good about turning point form is you can look at the equation and just take the turning point straight from it. All right. So the opposite value of h and that value of k remains the same. Now, one thing that is good is that you can turn, I shouldn't say turn, using turning point form. You can convert standard form into turning point form by completing the square. So when you see an equation in standard form, y equals ax squared plus bx plus c, you can actually turn that into, or convert it into turning point form by completing the square. Remember, completing the square, you need to add the value of b over 2 all squared, and also subtract the value of b over 2 all squared to balance that equation. And this part of the equation will give you, not that part there, not the minus, this part here of the equation will give you a perfect square. Okay, so that's how you can convert standard form into turning point form. Again, I'm not going to go through an example of that. You can watch one of my other videos if you want to see how to complete the square or factorize by completing the square to move from standard form into turning point form. Alright, now just the other few things I wanted to show you guys with some of the formulas we've been looking at. So there's a formula for the axis of symmetry. Remember, these you'll all be looking at standard form. So in the terms of y equals ax squared plus bx plus c, if you want to work out the axis of symmetry, the formula is x equals minus b all over 2a. So substitute the values from b and a into this equation. Alright? Obviously b and a. Whatever that value is will be your axis of symmetry. The funny thing about the axis, or the good thing about the axis of symmetry is the axis of symmetry is the same as the x value in your turning point. So if I go back here, just quickly, here's my vertex, okay, 2, 3. For that one, my axis of symmetry is x equals 2. Here's my vertex, -4, -2. My axis of symmetry is x equals -4. So the x value in the vertex is the same as your axis of symmetry. That's why there's no point, or there's no real need to use the axis of symmetry formula when you've already got turning point form, because you can read it straight off of the turning point, or straight off of the vertex. You're only really using that when it's in standard form. That's why the formula involves, the value of b and a. Alright, discriminant formula. Discriminant formula is just used to determine how many x-intercepts there are. The formula is, we use delta to determine how many intercepts there will be. So delta is equal to it's b squared minus 4 times a times c. And again, you're just taking those three values, b, a, and c, straight from standard form here. Okay, and substituting them in. If delta is, and this is really important here, if delta is less than 0, there are no x-intercepts. If delta is equal to 0, then there's only one x-intercept. You'll notice that it'll be a perfect square. And if delta is greater than 0, there are two x-intercepts. Okay, so you can use that formula to determine how many times that parabola will cross the x-axis. Now, the other thing we've used is the quadratic formula. Again, you're just taking values from standard form and substituting them in. You remember the quadratic formula from when we were doing quadratics, hopefully, is x equals minus b plus or minus square root of b squared, take 4 times a times c, all over 2 times a. And I guess visually showing you this is what that means, that the plus and minus, the plus and the minus are the two intercepts. So this is the plus, so minus b plus root b squared, take 4ac all over 2a. And this is the minus, okay, minus b, take b squared, take root b squared minus 4ac all over 2a. They're the 2x intercepts. Okay, so there's actually a few ways. If you've got standard form or an equation that's in standard form, let's just look at this one for example. Y equals, let's just keep it simple, x squared plus 7x plus 10. You know, we can substitute the values of a, which is 1, b, which is 7, and positive 7, and c, which is positive 10, into the quadratic equation to determine what my two x-intercepts are going to be. There will actually be 2 for this one. Or you can factorize it. But again, I'm not going to show you that in this video. I've got other videos up that will show you those things. So I really just wanted to show you this video create this video as a bit of an overview of the things we've looked at. So the key features, you know, what's great about standard form, what's great about turning point form, why we actually bother with completing the square. Okay, remember that's to convert standard form into turning point form. And then the 3 formulas that we've looked at, the axis of symmetry, the discriminant formula, and the quadratic formula, guys. So I know it's quite a long video, but yeah, if you've watched it all the way through, thanks for watching. And yeah, if you're after more information, then search up some of my other videos to help you in this topic. Okay, cheers.